And thank you for inviting me to give this talk in this nice conference. Unfortunately, I haven't attended many of these talks, but I try my best to present mine. So this work is already available on the archive. We posted it last month. And it's a collaboration with two fantastic colleagues, Yasunori Lee and Kantaro Omori. One is my current student who is going to get PhD pretty soon. And the other is my former student who recently got an assistant professor position back in University of Tokyo. So what we did is that we studied how higher symmetries match across one of the 4D n equals 1 supersymmetric duality. So the higher symmetries, one form symmetries and two groups, etc., which Sakura talked about. And I'd like to consider these things in the context of 4D quantum field theories with n equals 1 supersymmetry, right? And we examine this in the context of Intriligator-Seiberg duality. That's the duality between SO gauge theories with a number of flavors. So originally, I thought of calling this duality SO-Seiberg duality, but I had a chance to chat with Intriligator, and he objected me in calling it as SO-Seiberg duality because it was found in a paper by Ken Nati. So I'm calling it an Intriligator-Seiberg duality. So let's start. But okay, yeah. So I really don't remember exactly what I wrote. So this project took such a long time. You know, a few years ago, we know that this thing called higher symmetries, one form symmetry and two groups, became gradually popular, right? And I like this stuff, but I also like supersymmetry dualities. So it's a natural thing to try to combine both of them. And the natural place to try is to consider SO gauge theories, because there you have both flavor symmetry and one form symmetries. So I thought that somebody will quickly do that, but nobody has done that. So we started thinking about it, but it took about 2 years of thinking on and off, which had many ups and downs, mostly downs, mostly for Yasunori, because I forced him to do many complicated Bourdism computations, which he obliged to do. Then, but anyway, so there was a long story, up and down, but I tried to present this work today in a somewhat logical point of view. Let me proceed. So first, I would like to review one form symmetries and two groups from a rather basic starting point. And also, I need to remind you about Intriligator-Seiberg duality. And then I'd like to describe how they are combined. So there will be some overlap with Sakura's talk, as far as I attended her talk earlier in this conference. But let me try to review the concept of higher symmetries, because I don't think everybody is familiar with this concept. So let me start with higher symmetries. So please ask me questions anytime. So let's start by reminding ourselves what the ordinary symmetry is. So take a symmetry element G in a group G, and let's take 4D as the standard example. So one way to visualize what's going on is that a point operator O crossing a three-dimensional wall labeled by G. So let's say G is the simplest group, Z2. And if operator O crosses this wall, implementing the group operation G, operator O becomes GO, right? And if operator O is even, nothing happens. But if the operator O is odd, you get the sign -1, right? So that's how you try to visualize the action of finite group, for example, on operators. So you can try to generalize that, and you can consider symmetry acting on not point operators, but line operators. So the blue line here is the line which is acted on, right? And the role of the 3D wall is now played by the 2D wall linking with this one-dimensional line. So I draw drew it using black color. So what happens is that if this 1D line crosses this 2D wall, you get some effect. So that's a generalization of what we saw in the last slide. So this is supposed to be happening in 4D, which is a bit hard to imagine. So let me try to project the figure into three-dimensional space. The projection looks different depending on exactly how you project it. So if you project along the time direction of this world line, the world line looks like a point, and you just cross this point, blue point, across 2D wall within 3D space, right? Another way to project it down to 3 dimensions is to keep this one-dimensional line as blue line, while you, try to project this 2-dimensional sphere into a 1-dimensional line. So what happens is that you have 2 lines linking each other, and you slice them, and eventually they becomes topological different configuration, and that's what happens. So there are 2 different ways of viewing it in 3D. So, a Pform symmetry is a symmetry which acts on p-dimensional objects, right? So the zero-form symmetry is the standard one, where you have point operator crossing a 3D wall, a codimension 1 wall in general, and that wall does something to the operator. And similarly, in the case of one-form symmetry, what is acted on is a line, and you act on it by a 2D wall. And if you cross it, you have some effect. So that's introduced by Gaiotto, Kapustin, Seiberg, and Willett several years ago. So that's the one-form symmetry. And let me briefly explain 2 groups next. So you know that zero-form symmetry groups can be extended. So a group G can be extended by a group H to form a bigger group gamma, right? So that's something you know. But it is known that zero-form symmetry can also be extended by a one-form symmetry to combine into something non-trivial, which is usually called a 2 group. Here, the square bracket 1 is a reminder that the group A is now regarded as a one-form symmetry, and you have some mysterious combination, which I will explain in more detail next. So the first 4D gauge theory example where this 2 group appears was found by Shin and Lan last year. So that's, but they are quite abstract, right? So let me try to give it more concreteness by seeing some examples. So the easiest 4D theory, which has one-form symmetry, I think, is pure Maxwell theory, pure SO2 gauge theory. And it has a continuous one-form symmetry, but let's take just a Z2 subgroup because that's the only thing we need later. So it has 2 Z2 one-form symmetries. One of them is electric Z2 one-form symmetry. So in Maxwell theory, you can consider Wilson lines of charge Q, right? And you can consider a 2-dimensional wall such that if the line of the Wilson line crosses this wall, you get the sign -1 to the charge when you make the line crosses the wall. Similarly, this Maxwell theory has magnetic Z2 one-form symmetry such that if the wall crosses a Tohoft loop of magnetic charge M, you get the sign -1 to the M depending on the parity of M. So there are 2 types of one-form symmetries in Maxwell theories, electric and magnetic. So this is just a picture again of what's happening in the case of electric one-form symmetry. So you have a Wilson line with charge Q, you have a 2-dimensional wall implementing the symmetry, if they cross each other, you get the sign, which is -1 to the q. So let's have some better idea of exactly what this symmetry implementing two-dimensional surface, right? So this is a picture of what's going on. So in one-dimensional, in the projection down to 3D. So you have a two-dimensional wall, and you have a line, and you pull this up, and pull this out to this configuration, right? And what I'm saying is that you get an additional factor of -1 to the q in the process. So to realize that, what you see is that if you consider a small Wilson line around this black surface, this needs to produce the phase -1 to the q, right? This means that this specifies the holonomy of the Maxwell field around this circle. So this means that the integral of the vector potential around this difference of two curves, which is the very small curve around the black curve, is exactly 1/2, right? So if you have 1/2 holonomy, then if you raise it to the power exponential 2 pi iq, you get exponential pi iq, which is -1 to the cube. So what you learned is that this black two-dimensional wall implementing electric Z2 symmetry, electric Z2 one-form symmetry of Maxwell theory, is a surface around which you have a half flux of the magnetic field. So that's what physically is going on. So that's the electric case. For the magnetic case, again, you have a 't Hooft loop, which has charge m, and you have a 2D wall implementing that magnetic Z2 symmetry. And if you bring it out, you get this sign -1 to the m, right? So what is this green wall? How do we implement it? So it's again easy. So we use a different projection in this case. So if the line or the point, which was originally a 't Hooft line, is inside the sphere, you get something. And when it is outside, the value needs to change, right? And you remember that if you integrate the magnetic field around the sphere surrounding the 't Hooft loop, you get m when this is inside, and it is 0 if it's outside. I mean, it's just a Gauss law for the magnetic field. This means that the green wall realizing the magnetic Z2 one-form symmetry is just an integral of the magnetic field. I mean, evaluated on top of this green wall, right? With this factor pi I. So you can evaluate this factor on this side, which gives you -1 to the m, right? Because this is m. On the other hand, if the 't Hooft loop is outside, the integral is 0. So there's a relative sign factor difference of -1 to the m. So this way, you have a better physical idea of what are the walls for the electric Z2 symmetry and magnetic Z2 symmetry in the case of Maxwell theory. So for the electric Z2 one-form symmetry case, the black wall, two-dimensional surface implementing it, has a half unit of magnetic flux around it. I mean, you need, because we are in a 4 dimensions, there's a small one-dimensional circle linking with the sphere, right? And if you integrate the vector potential, you have half the flux in it. So that's the electric Z2 one-form symmetry wall. So as for the magnetic Z2 symmetry, the wall implementing that Z2 action is just an insertion to the path integral of this factor exponential pi I of the integral of the magnetic field. So these are the two realizations, very concrete realizations of Z2 implementing walls of Maxwell theory. And now there's an interesting issue. If you insert both these green wall and the black wall. So this black wall is the Z2 implementing wall for the electric one-form symmetry, and green is the same for the magnetic one-form symmetry. In 4D, two 2D surfaces intersect generically at one point, right? So there's an intersection point, but you have a problem defining exactly what the contribution is. This is because of the following. As I said, I'm in this 3D projection picture, around this black line, you have a factor, you have a magnetic field of plus minus 1/2, right? But this green surface is an integral of exponential of pi I times this integral of b. Therefore, this intersection point of the two walls have a contribution, which is exponential of plus minus pi I divided by 2. And it can be plus I or minus I, but you cannot decide which one. So there's a plus minus 1 ambiguity if you insert both the electric Z2 wall and magnetic Z2 wall. So this is a plus minus 1 valued mixed anomaly between electric and magnetic Z2 one-form symmetries. So I just reviewed the fact that the two Z2 one-form symmetries of Maxwell theory has a mixed anomaly between them. I can give a mathematical derivation of that too, but here I just wanted to present it in a more physical way. So that's the case of Maxwell theory. But today's topic is the SO gauge theory, right, with flavors. So let me gradually make things difficult. So instead of Maxwell theory, which is SO2, let's consider SO2N gauge theory. So SO2N gauge theory still has two Z2 one-form symmetry. One is electric Z2 one-form symmetry. The other is magnetic Z2 one-form symmetry. The electric one-form symmetry does the following. You consider Wilson line in various representations, and we distinguish them into charge 0 and charge 1, modulo 2, right? And that's decided by how the element -1, -1, -1, diagonal element -1 of SO2N acts on it. So the vector representation has Q equals 1, but the adjoint representation has Q equals 0, right? So it's like NRDT in the SUN, but it's simpler in SON. Magnetic Z2 one-form symmetry is again similar to the Maxwell case, but this time the integral of magnetic field does not make immediate sense because it's a non-abelian gauge theory. But there's something called the Stiefel-Whitney class, which is a Z2 quantity. So the integral of that around S2 surrounding the Toho line, and that gives you 0 or 1. And that controls whether the SO2N gauge configuration lifts to spin 2N or not. So you can ask the following question. So there are similarly Z2 one-form symmetry implementing walls, both for the electric one and the magnetic one. And what happens if you insert both of them and let them intersect at one point? So the answer is that the partition function is ambiguous by a sign which is -1 to the power n. It's easy to derive it. You can do a formal mathematical computation, but physically, what you do is to start from SO2N, add some adjoint representation field, and break it to SO2 to the n. SO2N contains a subgroup SO2 to the power n, and each SO2 behaves exactly as I told you in the case of the Maxwell theory. So each SO2 subgroup contributes -1, and there are n such SO2 subgroups. Therefore, the total contribution is -1 to the n. So that's how you determine the anomaly, mixed anomaly between electric and magnetic Z2 one-form symmetries for the SO2N gauge theory. Now, I said that SO2N theory has magnetic Z2 one-form symmetry, which measures this Stiefel-Whitney class. So let's ask ourselves what happens if you gauge this magnetic Z2 1-form symmetry, right? What happens is that the charged lines with non-zero M is removed. I mean, gauging some symmetry removes charged objects from the spectrum, right? So M is always 0. This means that the gauge configuration SON 2n is always liftable to S spin 2n. So that's the definition of the Stiefel-Whitney class. This means that by gauging this magnetic Z2 1-form symmetry, the theory becomes spin 2n theory. So now let's consider the 1-form symmetry of pure spin 2n, right? So in this case, there are just electric 1-form symmetry, which assigns charges to the Wilson lines. And that is a generalization or formalization of what people have called center symmetries from the time immemorial. And center of spin 2n is always has 4 elements, but the form of the group is different depending on the parity of n. So spin 2n with n even has center Z2 times Z2, while it is Z4 when n is odd, right? So the considerations so far tell us the following. The SO2n theory always have Z2 times Z2 1-form symmetry. So this green one is the magnetic Z2 symmetry, and the blue ones are electric 1-form symmetry. While if you gauge Z2 magnetic symmetry, you transform SO2n into spin 2n, right? And in that case, when n is even, the electric 1-form symmetry is given by its center, which is Z2 times Z2, while when n is odd, the 1-form symmetry is Z4, as I said, because the center of spin 2n is Z4 in that case, right? And we also studied that this Z2 times Z2 1-form symmetry of SO2n theory has anomaly, which is 1 minus 1 to the n. So it is trivial. I mean, the anomaly is actually absent when n is odd. So in this case, it's without the mixed anomaly. But when n is odd, this is with anomaly. So this is the result of our explicit concrete analysis of spin 2n and SO2n gauge theories. But in fact, all these things is purely formal. So this statement always holds. So if you have Z2 times Z2 1-form symmetry without the anomaly, and suppose you gauge this Z2, this turns the theory into a slightly different theory with, again, Z2 times Z2 symmetry, again without anomaly. But if you start from Z2 times Z2 symmetry with a mixed anomaly of this form, and if you gauge the magnetic 1-form symmetry, then somehow the presence of the anomaly affects the gauging process, and the resulting symmetry is not Z2 times Z2, but it's a Z4. So that's something purely formal. So if you know the higher symmetry together with its anomaly, then you can answer what happens to the higher symmetry if you gauge some subgroup. So that's a purely formal feature without anything related to its dynamics. So it doesn't depend on any concrete model. So this is a generic feature. But I just showed the examples by looking directly into the systems. Okay, so I think we got some good ideas on 1-form symmetries. So let's move on to 2 groups, right? So let's consider a spin 2NC gauge theory with 2 NF flavors in the vector representation. So it's the standard SOQCD, but I just specify the global form of the gauge groups to be spin. So it has SU flavor symmetry, right? Acting on the flavors. So what is the 1-form symmetry, you ask? So as I said, the center of spin 2NC is always Z2 times Z2 or Z4, right? In particular, in the latter case, let's take a spinor Wilson line and take its square. So imagine SO spin 6. Spin 6 is SU4, right? So if you the spinor representation is 4-dimensional representation, and if you take tensor product of 4 times 4, it contains the 6-dimensional representation. It contains the vector representation. But what happens in this case is that we are now in a system with dynamical flavors, dynamical particles, which is in the vector representation of the gauge group. So those dynamical particles can attach to the Wilson lines to screen the charge. So the vector Wilson line is effectively screened and it becomes a trivial representation. Therefore, only the Z2 quotient group survives. So the vector representation, I mean, the Wilson line in the vector representation can always be screened in terms of the particles, dynamical particles. So they don't comprise a different class in the under the one-form symmetry. So it becomes trivial. So only Z2 one-form symmetry remains. So that's what you have if you don't care about the flavor symmetry. However, you need to remember the following fact. The dynamical particle you use to screen, so you imagine Wilson line in the vector representation, right? Wilson line in the vector representation, and you try to screen this vector charge by attaching a dynamical particle. But here we are using, we are considering the theory which is SOQCD, right? So each particle is in fact a bifundamental of SO gauge group times the SU flavor symmetry. So if you try, so you try to screen the charge of the Wilson line, and you can effectively screen the gauge charge, but it inevitably assigns some flavor charge to the Wilson line. So you cannot remove, although you remove the vector charge of the Wilson line, you added to it the fundamental representation under the flavor symmetry. So in particular, -1 is a non-trivial center element of flavor SU2NF, and that acts non-trivially on the Wilson line. So what happens is the following. So I was talking about the NC odd case. So if you consider S spin 2 NC with NC odd with 2NF flavors, what happens is that the square of the gauge spinor Wilson line is a gauge vector Wilson line, but it can be screened to gauge trivial Wilson line, but it adds a flavor fundamental charge, right? So this means that, I mean, if you start from 2 gauge Wilson lines and try to merge it, right? And as a gauge Wilson line, it disappears, it can disappear, but the flavor Wilson line remains. So this means that the one form charge, you started from 2 objects with one form charge, you combine it, it disappears as an object carrying one form charge, but the remaining line operator is non-trivial under the zero form flavor symmetry. So what happens is, so let me repeat, you started from 2 one form charged objects, line operators, you merge them, it no longer carries one form charge, but it carries a zero form charge. So that's what is going on. So this is the simplest case of 2-group symmetry in 4 dimensions. And you can try to formalize it mathematically, but the physics content is basically just that. So what we saw is that when NC is odd, one form symmetry and zero form flavor symmetry are non-trivially mixed, while when NC is even, I mean, if you take the square of gauge spinor Wilson line, it's just gauge singlet, so nothing happens. So in that case, 2 parts, I mean, the one form part and the zero form part stays separate. So let me say it in a different way, slightly different way. So what's going on is not that, in the case of 2 groups, what's going on is not really that arbitrary part of zero form symmetry is complicatedly mixed with the one form symmetry. As I explained, what happened is that if you take 2 gauge Wilson lines, I mean 2 objects, 2 line operated charged under the one form symmetry, you merge it, and it just somehow becomes a flavor Wilson line. So that's what is going on. So what is what we are doing is that from the SU2NF zero form flavor symmetry, you extract center symmetry of the flavor group, right? So in the past, people talk about center symmetry of the gauge theory to discuss confinement, etc. But you can try to extract center symmetry of the flavor group. So there is effectively a flavor Z2 form symmetry for this SU2NF, deciding how -1, the element -1 in SU2NF acts on the various flavor Wilson lines. And what's going on is that this original electric Z2 form symmetry and this flavor Z2 form symmetry can mix in a non-trivial way. So when NC is odd, what happens is that effectively these two form a Z4 group, while in the case of NC even, they remain as Z2 times Z2, right? So why is it Z4 in the NC order case? So let me repeat. So you start from gauge spinor line, right? And you take two gauge spinor line, you merge it. So this becomes gauge vector, and you screen it with dynamical particle. Now it's a flavor fundamental. And flavor fundamental has Z2 charge under SU2NF. I mean, it is odd under -1 in the SU2NF. So if you take two copies of that, that becomes completely trivial. So this means that if you start from 4 copies of original gauge Wilson line, they become trivial, which is why this is Z4. Okay, so for spin 2NC and SO2NC theories with 2NF scalar flavors, what we found can be summarized as follows. So in what we just saw is on this left-hand side. So in the case of a spin 2N theory, when N is even, what is going on is that you have Z2 electric one form symmetry, and you had SU2NF flavor symmetry. But what is what is important is just the Z2 center symmetry of SU2NF, and they stay separate when N is even, but they become combined into Z4 when N is odd. So that's what we found. And you can do the same exercise for the SO2N theory. When the flavors, are not fermion but scalars, and you just basically have Z2 magnetic one form symmetry and the Z2 flavor one form symmetry, and this is what we have. So again, red Z2 is electric one form, green Z2 is magnetic one form, and finally yellow Z2 is the flavor one form symmetry, which tells us how the flavor Wilson lines transform under the subgroup ±1 of SU2NF. But the fermions affects all these things. So if you remember what I discussed about the symmetries of the pure SO2NC theory, which I redraw here, these two look basically the same, right? So what happened is that in the pure Z2, pure SO or spin case, you had this blue factor of Z2, which was an electric one form symmetry. But this part is usually considered to become trivial if you add flavors, because these measure the Wilson lines in the vector representation, but it can be screened by the dynamical particle. But by considering the flavor symmetry charge of that screening particle, you can, in some sense, resurrect this Z2 as the flavor one form symmetry of the SU2NF group. So basically, pure SO or spin theory behaves the same way with QCD, if you also consider the SU flavor symmetry. So that's what's going on. But fermions will change many things, as we will see. So that's the review of the. Yes, please.
Can I ask a basic question? I'm a bit confused about whether I should yeah, in your last line, the slides after, I guess, but whether I should think of this Z2 flavor as a one
Right.
form or zero form, because it's one form, it's still zero form because it acts on some local operators, but it's also, in a sense, I mean, the way we define it, it's pretty much like a one form symmetry, but on the flavor, on the background line, on the flavor line.
Mm-hmm.
So
that's a very good question. Yeah, I should have made this clearer. So here, what's going on is that you start from two gauge Wilson lines, right? And you merge them, and it becomes a flavor Wilson line. So it doesn't become a flavor charged point operator. So you should think of it as a one-form symmetry. Yeah. Another more formal way of understanding it is that the total group combining gauge and flavor part is not spin 2n times SU2NF, right? Because by fundamental field transforms non-trivially under the combined center. So the entire group has a structure spin 2n times SU2NF divided by Z2. Okay, therefore, the flavor symmetry is not quite SU2NF, right? In fact, it's SU2NF over Z2. And therefore, there's no point operator charged under plus minus 1.
I see.
Yeah, so it's not a zero form symmetry, but the flavor Wilson line in that charge sector remains. So that's the reason why Z2 subgroup of zero form symmetry is somehow upgraded into one form symmetry. Thank you for the question.
Thanks.
Okay. So let me go to the review of the Intriligator-Seiberg duality. So that was basically the review of the Shin and Lam paper from last July. Sorry, July 2020. So Intriligator and Seiberg found in 1995 the following duality. So for the n equals 1 gauge theory with SO2NC gauge group with 2NF flavors is dual to basically the same thing, but with the color changed to 2NF minus 2NC plus 4 with some superpotentials, right? And there are many checks, as you know. I mean, of course, the zero form symmetries match, the anomaly polynomials match, the operators match, and slightly later, people realized that you can compute something called superconformal index. They also match. So far, so good. But how about the global form of the gauge group? So there's an early work in 1997 by Strassler, who suggested that, in fact, this Intriligator-Seiberg duality exchanges SO and spin. But that didn't quite uncover the whole story. So what he did was to consider the Seiberg dual pair in the presence of massive spinor matter. And he found that the massive spinor particle on the electric side, in fact, maps to monopole operators on the dual side. So it's a really interesting work done in the rather early days. And if you take the infinite mass limit, you can rephrase what he did as the study of the fate of the Wilson line in the spinor representation under the Seiberg duality. So that was done in my paper with Ofer Aharon and Nati Seiberg in 2013. I cannot believe that it's only 80 years ago, but that's the fact. So in order to state the result correctly, you need to realize that there are not just two, but in fact, three types of SO gauge theories. So there's spin theory, there's SO plus theory, and there's SO minus theory. So the differences among them lie in their line operators. So the spin theory has Wilson lines. So the horizontal axis is electric charge, and the vertical axis are magnetic charge in some sense. And they are Z2 times Z2, but I drew them as if it's Z times Z. So spin theory has a Wilson line in the spinor representation, but SO theories don't have Wilson lines in the spinor representation. Instead, they have 't Hooft lines, which have non-trivial Stiefel-Whitney class. So that's the standard SO plus theory. But SO minus theory is such that the 't Hooft line automatically has electric charge. So it has a dionic line. So these three cases are distinguished by whether they have Wilson line or 't Hooft line or dionic line. So under the Intriligator-Seiberg duality, as it is known that the Higgs vacua exchange to confined vacua. So this dynamical information can be used to tell how the Seiberg duality acts on the three choices of the global form of the gauge group. Of course, in the Higgs vacua, Wilson line follows perimeter law, 't Hooft line follows area law, and dionic line also follow area law. In the confined vacua, what happens is that the Wilson lines have area law, and the 't Hooft line also has area law, and dionic line has a perimeter law. So this is somewhat strange, because naively you would think that in the confined vacua, 't Hooft line has perimeter law and dionic line has area law. But due to the funny feature of the Seiberg duality in the SO case, in fact, the supersymmetric vacua is obliquely confined. So it has the perimeter law. I mean, dionic line has the perimeter law. So this is the matching. So what's going on is that the spin theory is sent to SO minus theory, SO plus theory is sent to SO plus, and SO minus is sent to spin under the Intriligator-Seiberg duality. And this has been checked by computing the superconformal index on the length space by Razamat and Villet. So they have a Mathematica code also posted on the archive, so you can download it and check the agreement to arbitrary degree available on your computer. So it's pretty well tested. So the question is whether the two group structure agree. So that's our question. So I'm running out of time, I know, but I will just skip the last section, so don't worry. So let's talk about higher symmetries in Intriligator-Seiberg duality. So let's, in fact, we have already answered the two group structure in the case of spin gauge theory, right? So let's remind ourselves the argument. So you start from a gauge spinor Wilson line, which has a Z2 charge under the electric Z2 one-form symmetry. So you take two copies of that, and it becomes gauge singlet when NC is even, but it becomes gauge vector when NC is odd, just because of the difference in the tensor product rule in the representations. But the gauge vector can be screened by the fermion, right? And it becomes flavor fundamental, because our particles have vector charge under the gauge group and the fundamental charge under the flavor symmetry. Therefore, the Z2 one-form symmetry and the SU2NF zero-form symmetry remain separate and direct product when NC is even, but it forms a non-trivial two group when NC is odd, right? So you need to do the same analysis to tell what happens in SO NC plus minus, right? So what happens is that you need to take charge 1 to 't Hooft line, which is charged under the magnetic Z2 one-form symmetry. You take two copies of that. That's charged 2 to 't Hooft line, and that can be screened by a dynamical monopole, right? So you screen by dynamical monopole, it becomes trivial line, but trivial in the sense that it doesn't have gauge magnetic charge, right? But this screening monopole, the dynamical monopole used to screen the charge 2 to 't Hooft line can have flavor symmetry charge, right? So if this dynamical monopole has a fundamental charge, then this resulting line operator has fundamental charge under flavor symmetry. So depending on whether the dynamical monopole used to screen the charge 2 to 't Hooft line has charge +1 or -1 under the -1 of SU2NF, the Z2 one-form symmetry and the flavor zero-form symmetry can either remain a direct product or combine into a non-trivial two group. So that's how it works. So the point is that there can be fermionic zero modes on dynamical monopoles, potentially inducing flavor charges on them. So many people in the audience will be familiar about that. So a famous example is n equals 2 SU2 with NF flavors, right? So each monopole carries fermionic zero modes coming from the flavors, and they need to be promoted to gamma matrices of the flavor symmetry. So monopoles transforms into spinor representation of SO2NF. So it has a rather strange transformation law under the center of SO2NF. And our situation is similar. So the question boiled down to the following. In SO2NC gauge theory with plus minus with 2NF flavors, how do dynamical monopoles transform under -1 of the SU2NF flavor symmetry, right? So that's a monopole physics question, which can be answered if you are old enough. I mean, yeah, because it's done a long time ago. So it's fun in itself, but the quickest way again is to break SO2NC into SO2 to the power NC, because these are anomalies, so it's unaffected by various deformation as long as it doesn't break the symmetry. So you add adjoint fields, break it to the Cartan subgroup, right? You have fifth Polyakov monopoles. You can analyze the fermion zero modes, and you can quantize them. Done. So the flavor charge of the monopole under -1 of SU2NF is -1 to the power NF for SO2NC plus theory. And it turns out -1 to NF plus N minus NC for SO2NC minus theory. So that's what you find, right? So we conclude the following. The Z2 one-form symmetry and the flavor symmetry become two groups in these green elements. So the answer depends on whether the global structure is either spin or SO plus or SO minus, and also whether the parity of NC and NF, right? So in the case of spin theory, whether the result is two group or just a direct product just depends on NC, right? Because it's just determined by how two gauge spinor lines combine into gauge singlet or gauge vector. So it's just non-trivial when NC is odd. Similarly, in the case of SO plus, as I said, that the monopole has non-trivial flavor charge only when NF is odd. So that's here and here. And SO minus case is this, right? Now the Intriligator-Seiberg duality acts as SO2NC, sending it to SO2NF minus 2NC plus 4, and exchanges spin and SO minus and keeps SO plus. So this is how the Intriligator-Seiberg duality acts. And lo and behold, I mean, product is mapped to product, two group is mapped to two group in a rather non-trivial way. So that's what we found. And I just ran out of my time, but I kind of expected it. So this was analyzed using how the flavor charge of the monopoles, right? But you should be able to obtain this by just analyzing the fermion anomaly, and that's explained here. But if you are interested, you can have a look at our paper or in the slides. So I already uploaded the slides online, so I can give you the URL. So I just reviewed one-form symmetries and two groups, and we studied them in the case of SONC with two NF flavors. And they are mapped as expected under the Intriligator-Seiberg duality, right? And I didn't have time to explain it, but our results indicate that there are very subtle global anomalies of fermions. So that's it. Thank you very much, and please ask me questions.
Thank you, Yuji. Questions?
Can you say more about that subtle global anomaly?
Pardon?
Can you say more about that subtle global anomaly?
Right. So here in the talk, I explained how to derive the two-group structure by a physical consideration, right? But you should be able to understand it in a rather formal way. So the formal consideration shows us that in order to have that two-group structure for those particular choice of NC and NF, that means that fermion in the representation, vector representation of SO2NC times the fundamental representation of SU2NF has a global anomaly under the combined group, which is SO2NC times SU2NF, right? So it's kind of like a generalization of Witten's anomaly. So for SU2, we know that there's Z2 global anomaly of Witten, right? Here, it's a version of Witten anomaly. So the simplest case is to consider SO2N times SU2 over Z2. So if you consider fermions in the vector representation of SO times doublet of SU2, it has a certain global anomaly. It has to have that in order to reproduce those two-group structure. But that particular anomaly was not determined in the past. In fact, we were not able to compute this global anomaly for the most general case because of the complexity of the computation of the global anomaly using spin Bordism groups, etc. So, but that's what it has. So let me summarize it in one sentence. Our physical analysis requires that the fermion, bifundamental fermion under SO times SU should have a certain global anomaly, which should be checkable. We try to check as much as possible, but we haven't finished checking it. Yeah.
Yuji, is this anomaly you mentioned at the end, is it a discrete gauge anomaly, just like Witten, so that it leads to inconsistency?
It's a mixed anomaly. Yeah.
Okay. With
it's
global
like,
and gauge.
Yes. So it's like, I mean, very original anomaly was the mixed anomaly between the chiral symmetry and the gauge symmetry, right? So yeah, so it's a mixed gauge flavor global anomaly. So that's kind of new.
People think I'm very old if I ask you this question because you labeled that whoever knows zero mode very old. So I was a little bit, so this in the standard simplest SU2 two-polyarco monopole and fundamental fermion, the zero mode story is such that it's sort of mass dependent. If mass is sort of larger than the scale of the monopole, you don't have any zero mode. If it is less than, you do have this zero mode and doublet state thereof. I didn't see the mass story during your talk. So is there something more to elaborate on that?
I'm sorry about that. I should have said that I always consider the massless QCD.
Okay.
Yeah.
Thank you.
So if you make it massive, if you make it massive, you cannot keep the whole SU2NF symmetry. And flavor symmetry also becomes SO2NF, right?
Right.
Yeah, so the flavor gauge structure is not SO times SU divided by Z2, but rather SO times SO divided by Z2. And in fact, if you restrict to that subgroup, this anomaly vanishes. Yeah. So once you allow non-zero masses, this rather subtle anomaly just disappears and everything becomes very simple. Yeah.
I understand.
Thank you.
Any other questions? Comments?
So, sorry, yeah.
Jaewon first say. Then
I remember. So whenever you have this mixed gauge global anomaly, like GFF is non-vanishing, then there's two-group structure, which is the case for Maxwell's theory. Is
That's
this similar in that sense?
Yes, that's basically the same. Yeah.
How do I see this?
Well, so the formal analysis is exactly the same as in that case. So if you start from the mixed anomaly, then if you try to gauge the gauge part, usually you just discard the flavor symmetry as a symmetry, right? Because of the non-trivial mixed anomaly. So in order to save the flavor symmetry, you need to restrict the gauge part so that the mixed anomaly vanishes, right? So you need to put this extra condition on the gauge field to make the flavor symmetry survive. But that restriction is imposed by promoting the flavor symmetry structure of the gauged theory to be not just a direct product, but a two group. Yeah, so that's how it works. So at the formal level, in the past, there's a paper by Intriligator and Cordova and Dumitrescu about how the two group appears in the continuous mixed anomaly case, but it's basically similar. Yeah. So you just replace U1 one-form symmetry by Z2 one-form symmetry, and the analysis goes through.
I think Katsuya had a question.
Yes. So fermions also have this just part about the triangular anomalies of SU flavor. So do you expect that the answer is just the direct sum of Geta invariant and this one? Or?
That's a very good question. We don't understand. I should have said that we only considered USP2NF subgroup to avoid this issue. So if you, so SU2 isn't affected by this subtlety, but once the flavor is more than 2, there are triangle anomaly, and it's very difficult to distinguish the effect of global anomaly and perturbative. Yeah. But you can clearly see this discrete anomaly by just restricting the flavor symmetry to USP2NF.
I see.
In fact, in order to carry out this monopole analysis, I needed to add a joint scalar field to the system and couple it to the flavors. And that deformation, in fact, breaks SU2NF.
I see.
NF. Yeah, it just as in n equals to supersymmetric case. So yeah, I should have replaced every occurrence of SU2NF by USP2NF. That should have been more honest of me. But just for the familiarity, I didn't do that. It's like cheating. I'm sorry about that.
Thank you very much.
Okay.